was roped into this quite at the last minute, and I am thrilled to have the very last slot at the end of a very long day. So I will not be keeping everyone very long, I promise. And yes, I'm just going to introduce basically a bit of an overview of some of the organizations that I represent here and the work across Scotland in the quantum domain, but with a particular look at the University of Glasgow, what's going on there, and some of the, I think, interesting work there, and perhaps you'll agree. So just to kind of set it in a bit of context briefly of the UK ecosystem. So the government, even after the fairly recent change of government, has committed to investing £2.5 billion into the quantum ecosystem. And in terms of private money coming in, it's second in the world for private investment. Now, a third of that funding to quantum technology comes up to Scotland, even though it's only about 8% of the population. So it kind of punches way above its weight in that sense. And I think of particular interest in the fact that there's a huge strength in photonics industry in Scotland. And the idea for a lot of the work, I think, should be to capitalize on that and use that as the bedrock for what's coming in quantum. So I represent a few organizations here, but the first one is the Quantum Arc, and I'm going to come to discussing exactly what they are. And the second is the Quantum Computing Applications Cluster, the QCA. They're the ones who actually dragged me along here and forced me to give talks and things like that. So the QCA cluster, very briefly, it's basically connecting what we call the central belt of Scotland, and particularly Glasgow, Strathclyde, and the University of Edinburgh. So the idea is to match the hardware expertise in the likes of Strathclyde and Glasgow with the software work that goes on in Edinburgh, and basically to bring that together. And I think that there is has been a real lack of communication between two such impressive institutions, or three impressive institutions, in the work that's going on. So how do we actually merge that together to come up with some real applications and some real breakthroughs? Now, the Quantum Arc, the ones who actually pay my wages, we are a network funded by the Scottish government, with the idea being to build the network of quantum technology researchers across Scotland. And the remit is extremely broad. It involves outreach, bringing universities together, industrial partners together, education. So a lot of things going on. Basically, make it up as we go along. The remit is that broad that we can just kind of see what needs to be done and try and meet those needs. So yeah, promote the capabilities of Scotland is one of the remits. One of the reasons I'm here downstairs talking to people about how good Scotland is. And some of the interesting stuff that we do is engage with groups not usually associated with quantum. So in that sense, we recently had a quantum healthcare summit where we took about 50 or 60 people from the NHS, the National Health Service in the UK, who have absolutely no idea what quantum is, despite one of the government's quantum missions being that by 2035, every NHS trust will have quantum technology. When you talk to doctors, nurses, NHS managers, they don't know what quantum technology is. So it kind of grew out of that idea of, well, let's understand what the problems are in healthcare, understand what the capabilities of quantum tech are, and where the crossover is. And it was a fantastic, really, really interesting event, because we really, as quantum researchers, physicists, we got to understand where the bottlenecks in the healthcare system are, what are the problems, and we can start to map those to the capabilities or the potential of quantum tech in general. Now, a slightly more odd event we did was to gather a load of artists, from musicians, visual artists, videographers, everything across the board, and match them with quantum researchers. And I can't really remember what the idea was, that we just thought it was going to be something that might be interesting, and it really was. So what you see here is like a speed dating session, basically, where an artist will sit with a quantum researcher and they will try and understand each other and see if there's anything useful or interesting that can come out of it. And so we actually have a pot of money to fund ideas that come from our workshops like this. So there are currently a couple of artists are working with the Quantum Software Lab in Edinburgh, and they're going to produce some art next year. We have some visual artists who are going to make some animations. We have physical artists, sculptors, who are going to make some quantum sculptures. Please don't ask what that means. I have absolutely no idea. But that's the idea, is to kind of reach out to groups, basically as part of our outreach mandate, to explain, demystify quantum. It's not as complicated as many of us physicists would have people believe. There's no reason everyone can't actually engage with quantum and understand quantum. And then finally, facilitate quantum education and outreach. A lot of work with schools, kids in particular, is something we want to do, again, to introduce these quantum concepts early. You know, there's a lot of talk here today and in general about the lack of a quantum workforce. And one of the big barriers we see in the university is when we go to engineering departments and say, you know, you do electronic engineering, you're very good at all the stuff that we need to do, why not join a quantum lab? And they go, oh, no, quantum's not for me, it's too much, it's too difficult. But there's no reason that has to be the case at all. So introduce these concepts early, get people comfortable with them, and then we'll have that workforce. This is a lot of information I'm basically obliged to put up on the screen to describe how good the Centre for Quantum Technology at the University of Glasgow is. It's very good, a lot of research, a lot of very impressive academics, and a lot of money. You know, fairly standard stuff, but very good work coming out of the University of Glasgow in that sense. Now, one of the great strengths of the University of Glasgow is the James Watt Nanofabrication Centre. So, huge by the standards of public clean rooms in the UK anyway, clean room facility that has a fantastic amount of research and industrial work coming out of it. So, just some quick stats there: 32 staff, 170 users, 200 customers and collaborators. And we train about 100 PhD students every year and about 150 master's students as well. So it's an incredible education resource, academic resource, but also an industrial resource. And Kelvin Nanotechnology, who I'm going to mention shortly, they are the commercial arm of the JWNC. Now, they are a fully commercial company, but they're owned wholly by the university. It's an interesting model whereby, even though it's an academic clean room in theory, that's how a lot of commercial work actually comes out of it. And it underpins a lot of what I'll talk about in terms of commercialization and potential spin-outs out of the university. So just a brief overview of exactly what comes out of the James Watt Nanofabrication Centre. It's a huge variety of stuff. Every time a new PI arrives, they have big ideas for how to use this clean room, and they just try and make it happen. So a range of things from photonic sensors, obviously quantum tech, right down to power electronics. So Kelvin Nanotechnology, KNT, now they're this interesting company that I talked about where they basically manage all of the commercial projects within the university in terms of the clean room, in terms of the JWNC. So they've been long-time trading since 1997. Very, very credible, a real worldwide company at this stage, and over £100 million of innovation projects that they've partnered in. Now they're, basically limited often by just the size of the clean room. So there's a lot of work that they could be doing out there because, you know, they get approached a lot. The facilities that they have, that we have, are really, really high class. So 3 main areas: e-beam lithography, technology prototyping, production, and just generally quantum components. And then again, just some of the technology that they're actually involved in, from ion traps, gravimeters, to superconducting devices. So commercialization, it's a quantum business conference, so I'll talk about actually some of the commercialization that's coming out. Big areas of interest at the minute as Glasgow really shifts from, I would say, hundreds of years of being very pleased with itself about its academic track record and how good things have been going, to now being a lot more concerned with, okay, we actually have to keep up with some of the more dynamic universities and commercialize some of our technology, commercialize some of the stuff that's coming out of our fantastic academic research. So quantum sensors is a big area of interest from some of our researchers. There's a couple of spin-outs that the university is involved in coming out in that area. Superconducting qubits, something that particular I'm interested in. That's my research background. Cryo-CMOS control electronics, and then some future opportunities I'll give a quick nod to. So the first spin out that's coming very, very soon out of the university, it's basically going through incubation processes at the minute, involves superconducting quantum circuits, okay, and particularly qubits. We've heard a lot about these today. There's talk about the Rigetti Novara chip and Quantware and that. So the idea will be to use the expertise developed in the clean room over the last, I guess, 10 years of heavy research there about superconducting quantum technology and actually provide that as a commercial offering. Then Kelvin Quantum are another spin-out coming out of the Quantum Circuits Lab in the University of Glasgow, and they're on the control electronics side. So their basic aim is to use CMOS technology, standard CMOS technology, but cryogenically. Okay, there's again a lot of talk you see today or in general about how difficult it is to control quantum systems at cryogenic temperatures. So ideally, if you could take standard CMOS fabrication, well established, well understood, I mean industrial in scale truly, and use that to actually develop cryogenic CMOS, it would save a lot of the headache of trying to effectively reinvent the wheel. And the idea there is that the usual cutoff you can see here is rated to about minus 40 degrees usually, but they want to operate and do have devices that operate all the way down to 4 Kelvin, and they're currently testing to go down to the millikelvin temperatures that will be required for most quantum computing applications, or superconducting anyway. So the Quantum Circuits group then, which is the group that I was in for several years, a lot of nanofabrication for quantum, of course. So Josephson junctions, different types, and vertical interconnects. So again, a lot of research goes into the actual fabrication techniques, developing processes and recipes for how to actually build these superconducting devices. Measurements, although we have the group is broadly split into 2 parts, a large 10 to 12 people involved in the fabrication, about the same again involved in measurement, cryogenic measurement generally, and then cryo-electronics. So CMOS, like I said, characterization down to millikelvin, cryo-FPGA work as well, and SFQ, superconducting flux quantum devices, high-speed superconducting electronics. And interestingly, something that's been going on for the last couple of years is interconnects. How would you say, classical interfaces for quantum technologies. Okay, so how do we classically interface with quantum computing systems? And there's a really interesting project going on about optical interconnects, which is, I mean, great and something that I think will have to happen in the future, and a much more ambitious project to put wireless emitters and receivers inside a fridge and try and control qubits that way. It's ambitious, it's interesting, should we say. And then future considerations, we're looking at superconducting quantum error correction circuits. So obviously QEC is a major issue for quantum circuits in general, for quantum computing, and putting them on superconducting circuits would allow you to put them very close to the chip and would allow them to operate at very, very high speeds. So potentially alleviating some of the problems with quantum error correction. So we're working with University of Edinburgh on that one there, Quantum Software Lab. Miniaturizing cryogenic technologies. Basically, can we make them smaller, more efficient? A lot of healthcare technologies now coming out of the labs. Again, one of the reasons we wanted to have those discussions with healthcare professionals across the board was because there's a lot of interest in actually spinning out medtech, quantum medtech companies. And then finally, I mean, I don't think anyone wants to think about it at this stage of the day, but open to conversations and open to collaborations, of course. We have part of a couple of stalls downstairs, so do come and have a chat whenever you like. That's it, and I promise not to keep you very long, so there we go.
Thank you. Questions?
I got one. If you go back to when you said you spoke about with the, oh, thanks. You said you spoke with the NHS folks. Can you tell us a little bit more about the outcome? Like, what were they thinking about once you educated them about quantum computing?
Yeah, good question. So basically, I think, well, they didn't know what to think. They had no idea for a start. So they came in totally brand new about the whole thing. And they had, I guess, vaguely heard about quantum computing and how it was, I mean, I think in the lead up to the conference, they had looked into it and heard about quantum computing, how it was just poised to change the world and revolutionize everything. I think we had to politely explain that it's still a little bit away, you know. But the big problems that came out of it were, the big opportunities were in quantum sensing, first of all. It's going to very quickly go, that'll be the first technology that goes into the NHS or into healthcare. Quantum imaging, so medical physicists and radiographers were there and basically explaining what are the limitations and advantages of MRI or PET scans or CAT scans, and what are the limitations. So I can very quickly see how quantum sensors will go into hospitals, actually probably quite quick. They have huge issues with data and data processing, particularly in NHS, massive issues, which I had no idea about. Now, mapping the capabilities of quantum computing to their data problems is not necessarily straightforward. It could be done, but it will take a bit of time, one, to develop the quantum computing algorithms to get us there, but also then to map a lot of their issues with data aren't necessarily going to be solved by quantum computing until we can come up with how to map the problem with the solution, if that makes sense.
But they must have enough data to perhaps give insights that I'm guessing they're already deploying AI technologies to read their data. But I'm wondering if they're thinking along the lines of how do I further tap into this data that I have to get insights. Do you think they've thought that far down?
I think that the NHS is such a behemoth that trying to move it in any direction seems almost impossible. So individually, yes, they are thinking about that. For example, it's potentially, if you want to look at it commercially, one of the most richest data sets on the planet. It has since the 40s or 50s. It's been tracking everyone in the UK's medical data right till this day. It's an unbelievable resource if it gets tapped into. Now, it's also such a mess, some of it is in boxes in a warehouse and some of it is on computers and they use like 20 different systems. It's just such a headache. So it needs to be fixed first. And then, yes, there is huge potential in using it, huge opportunities, exactly.
Thank you.
No problem.
Thank you very much. Interesting to